So, Unit 8, Lesson 3, this is actually part 1. We're going to go back and we're going to talk about trig equations that look like this. If you remember about 3 tests ago, you would do things where I would give you restrictions. I would say solve for t between 0 and 180 degrees, or 0 and pi when we're using t. So if I give you a trig equation that says the tangent of t equals -1, one thing to note, I'm going to go back a slide here. Anytime you're asked to solve for x or t, we're going to solve on the interval from 0 to 2 pi. So all of your answers in radians will be within 1 revolution of the unit circle. If you are asked to solve for theta, again, 1 revolution of the unit circle in degrees is 0 to 360. So when I move over here, and I say the tangent of t is equal to -1, your thought process should be, okay, tangent goes back to, on the unit circle, y over x. In order to simplify to -1, what do we know about the values, the numbers that are y and x? If this fraction simplifies to 1, what do we know about x and y? They have to be the same. They can have different signs, but they have to be the same numbers. So where on the unit circle do you recall, do we always have the same numbers? The root 2 over 2s or the 45 degrees. All of those would be accurate descriptions of that. So now the key here is in what quadrants will tangent be negative? Okay, so there's the next piece that we had to put together. So up here in 2 and 4. So what are my 2 answers in radians that exist on 1 revolution of the unit circle? The 45 here and the 45 here, which are what 2 numbers? And 7 pi over 4. So those are the 2 answers that we're looking for. That's number 1. Now, pull out your calculator, because in another unit, we would set up a word problem, for example. We would determine that the opposite side and the adjacent side, so this would be O over A. We would write a trig equation, we would choose tangent, and then we would have to solve this. So what answer do we get when we solve this equation involving actual real numbers or real distances? How do we solve this in your calculator? How do you find an angle? Inverse. So in my calculator, I'm actually going to put in tangent inverse of 3.5 over 8. Please make sure you're in degrees, not radians. And what did we get when we put that in our calculator? Did you get 23.6, everybody? Okay. Now, this problem is not done. In the previous units, it was done. Right? But what I want to do is I want to talk about what we did up here and kind of extend it to what we're doing down here now. First thing, these problems as we set them up as trig equations are not application necessarily. They're general trig equations, all of which have to be solved between 0 and 360 degrees in the case of degrees. So if we come back up here to our radians example, do you remember when I said where is tangent negative and you told me it would be quadrant 2 and quadrant 4? If I come down here, just because I went to decimals and made it look a little bit different, tangent is positive or negative overall here? Positive. In what quadrants are tangent positive? 1 and 3. Okay? So if I think about this, I now am dealing with here or down here. Okay? For those of you that aren't paying attention, this is a really good time to check in because this is new information. This is a little bit different than what we did before. So notice we're still establishing which quadrants, 1 and 3. When we use inverses, they're only defined for acute angles. So we're talking about the reference triangle here, but we also have a reference triangle, which I'm going to draw in green, it exists in quadrant 3. So I know from solving the size of this angle is 23.6 degrees. Well, guess what the size of the angle over here is? 23.6 degrees. But I want to know what this entire value is. How much is that entire swoop? This little one's 23.6. How much is it if I start from here and go all the way around. 203.6. I actually have for this 2 solutions, not 1. Look. Does that make sense? Well, in the word problems that we always dealt with, they were right triangles, correct? But they weren't right triangles in the coordinate plane. They were just right triangles that we were drawing to establish real-world relationships. Now what we're doing is we're going to be setting up equations, right, and solving between 0 and 360 that we can have triangles, rather angles, that are bigger than 90 degrees. Okay, so that's where we use the reference triangles in quadrant 1 and quadrant 3, which we've done before. The new part is the fact that we solve using the calculator to find quadrant 1. Then we go back and we have to apply what we know to quadrant 3. No, not necessarily, because if I had given you like a negative in front here, your angles would have been quadrants what? 2 and 4. But now you're not going to give me negative answers. You're going to give me the positive and then all the way back around. We're going to do an example like that later on. But it depends on if it's sine, cosine, or tangent to define where the reference triangles actually are. So let's keep that in mind. That's all background information going into what we're doing now. Again, we're going to still use those restrictions. The restrictions aren't going to change for the entire unit. The rest of the unit, these are your restrictions. Okay? I will tell you none of your answers should be 2 pi or 360. How do I know that? Because these have parentheses here. They're the same thing as 0, so we would use 0 in place of those. Take a look at example 1. In example 1, 2 sine squared x minus 1 equals 0. We are solving for x. X, do you think it's going to be radians or degrees? It's going to be radians. So the key here is to identify the type of problem that this is. So if I, right above this, would change this into 2 s squared minus 1 equals 0. Okay, so I'm going to get rid of the trig part and just analyze the algebra part. What type of equation is the orange? It's difference of squares, but it's also linear or quadratic? Quadratic. Quadratic we solve by factoring, square root method, or quadratic formula. Okay, so this is what we did all the way at the beginning when we were reviewing the types of equations. Here's the reason why. If I have 2s squared minus 1 equals 0, wouldn't I solve this by adding 1 to sine squared x equals 1, dividing both sides by 2, sine squared x equals 1/2, taking the square root of both sides. How many solutions are generated when I take the square root? 2. Fundamental theorem of algebra is plus or minus. Now we get into our rationalizing. What is the square root of 1/2? The same thing as. Plus or minus the square root of 2 over 2 is equal to the sine of x. That looks like unit circle values to me. What do you think? This is why I said we've been building to this moment. Here it is. This is a quadratic trig equation. We solve this by isolating the term. The term is the sine squared x. Coming down, taking the square root of both sides, which generates plus or minus. Just as an aside, because I know some of you may not be asking me, the 1/2, the plus or minus, is the same thing as this. 1 over root 2 plus or minus is where I'm multiplying like this. So this is kind of all the work for what I have here, but that's where I got the rationalizing of the denominator. So now my question to you is, where on the unit circle do I have a sine value that is either a plus root 2 over 2 or a minus root 2 over 2? How many places does that exist? 4. 1, 2, 3, and 4. So what is x equal to? What values? Give me all of them in radians. Pi over 4. Keep going. 3 pi over 4. 5 pi over 4. 7 pi over 4. So what's crazy about this is it's only in that very last step. Do you ever use the unit circle? Everything else is really what you're being graded on now. Questions? Quadratic trig equation. Does anyone have a question where I got 4 solutions from? Or why there are these solutions? Here's your one shot for full explanation. Yep. Plus or minus 1/2, the square root of it, is the same thing as this, which leaves you with a root in the denominator. So you have to rationalize it. All right, example 2. Moving on. If I look at example 2, I'm going to get t plus root 3 equals 0. Agreed, this is a linear trig equation. No squareds. Okay, how do you solve to get tangent of x by itself? Minus root 3, correct? The tangent of x is equal to negative root 3. All right, so we're dealing with x, which means I want what? Radians or degrees? Radians, which means that I have to give you something that you can think out from the unit circle. So now let's translate this. What's the denominator? 1. If I write these, what did I cancel from top and bottom that were part of the unit circle values? These were all divided by what? These were all divided by 2. The other thought that I should have is the fact that this says here that tangent is negative, doesn't it? Say that right there. Tangent is negative. In what quadrants are tangent negative? Quadrant 2 and quadrant 4. So I'm going to need 2 radian values, one from quadrant 2, one from quadrant 4. And if I look up here, what is tangent in x and y values? Tangent is y over x, I heard that. So where do I have a y value that is root 3 over 2 and x is 1/2, finding your signs, in those 2 quadrants? The tall ones up here and the tall one down here. What are those 2 values? What's the tall one up top? 2 pi over 3. And down in the bottom, 5 pi over 3. Mind blown yet? Or are we feeling good? Well, do you remember when I would say to you things like, what is the tangent of 2 pi over 3? And in your head, you would go and you would find the y value and you would divide it by the x, and then you would cancel. Right, when you did the reciprocal, the 2's would cancel. We're working in the other direction. So I guess my thought process here is the fact that you would have done enough of them to know that if we're dealing with a unit circle value that has a root 3 in it, the only denominator that existed was a 2. And its counterpart for x also was divided by 2. Does that work? Like to do it that way? It's a loose connection, but because the unit circle is so limited in its values, there's only 5 numbers with different signs, it's easy to kind of work your way backwards. Easy relative term. Questions on number 2? All right, moving on, number 3. All right, example 3. I don't see any squareds in this problem, do you? No, I see none. Please put a note here. No, do not divide by trig terms. Write that nice and big. Do not divide by trig terms. Here's what I liken it to. If I have x squared is equal to x, why am I not allowed to divide by x? It reduces the solutions, right? It takes you from 2 solutions of the quadratic down to 1 solution. Same thing is true with trig. We cannot divide by sine x or sine theta in this case. So here's your reminder. How would I solve x squared minus x? I'm sorry, I just told you. How would you solve x squared equals x? Bring the x to one side, and then what? Factor it. X times x minus 1 equals 0, so my 2 solutions are 0 and 1. This is the theory that we want. This is what we do not do. So let's apply what we have here. Following what I did in variables, what would be step 1? Bring over the sign. So 2 sine theta cosine theta minus sine theta equals 0. Yes. This is the same as this. Now I move down one. Over here, I factored out x. What am I going to factor out of my trig equation? What's the same in both of these? Sine theta. Sine theta leaves me with 2 cosine theta minus 1 equals 0. Now, this is where those of you who do a lot in your head, sometimes you make up your own rules. How did I actually generate 0 down here as a solution on the far left? You take the first, what's on the outside, and you set it equal to 0. I'm going to do the same thing here. So the first thing I'm going to do, I'll do an orange. I'm going to say I want to take sine theta, set it equal to 0. And then in green, I'm going to do this part separate. I'm going to take 2 cosine theta minus 1 and set it equal to 0. So now let's think. Wait a second. Theta is degrees. Where on the unit circle do I have degrees equal to 0 for sine? Sine is x or y? Y. So I'm thinking to myself, where do I have y as 0? What 2 values? 180 and 0. So there's 2 solutions from the orange equation. Now when I go to the, yes sir. No, I said it can't be 360. If you're thinking 360, substitute 0 because they're the same, they're coterminal. Same thing. 2 cotangent theta minus 1 equals 0. This is linear or quadratic in green. Linear, so I'm going to isolate cosine theta. So I'm going to add 1, divide by 2. I get cosine theta is equal to 1/2. Cosine on the unit circle, x or y? Where is x equal to 1/2? X is equal to 1/2 at here and here. What are those 2 places in degrees? Pi over 3 in degrees is 60. That helps you here because you know this is 60. So what's that one? 300. Yes? All right, what questions do you have? Good so far? All right, moving on. Example 4. All right, so why do we have to do verifying identities? Well, number 1, we're going to get used to working with the trig terms and knowing how they stick together, like sine of x or sine squared x and what they mean. But the other reason is because we're often asked to solve trig equations that are mixed ratios. So if you look here, I have to find one that has sine squared with a cosine. As a strategy, we really don't like to have different ratios. In the last example, it worked out for us, but in this one, it's not going to. So do you have any suggestions for how I can get rid of one of these so that they're all in terms of the same thing? What can I do to substitute something out in order to have only one ratio? Yes, sir. identity. So my Pythagorean identity is going to replace sine squared x. Pythagorean identity, take out sine squared x, what goes in its place? Don't worry about anything else that's up here right now. Just tell me what sine squared x is as the Pythagorean identity isolated. 1 minus cosine squared x. There's my Pythagorean identity substitution. I then still have the 2, the minus cosine x, and the 1. Now I can go ahead and distribute the 2 and combine like terms. So I get 2 minus 2 cosine squared x minus cosine x equals 1. I chose to move everything to the right so that my cosine squared was positive. So I moved this, I subtracted 2. I think we're getting to this point, but I'm not sure from doing the verifying. If I get rid of the trig term and I just say 2c squared plus c minus 1, do you recognize that as a quadratic? How do I solve an equation equal to 0 that's a quadratic with 3 terms in that form? I could do quadratic formula, but what should I try to do first? Factor it, and it does factor. So if I go to factor this, I get 2 cosine x, I get cosine x. I need this to be a plus 1 in the middle, so I'm going to make this plus 1, this minus 1 equals 0. And just like every quadratic in the world, once we factor it into parentheses, what do we do with each of the parentheses? Set them equal to 0. So I'll take this one in orange. 2 cosine x minus 1 equals 0. Cosine x equals 1/2. Over here, I'm going to say cosine x plus 1 equals 0. Cosine x equals negative 1. And now I'm dealing with x again. So what do I get from the orange? X is radians now. Back to radians. X is equal to pi over what's 60 degrees? Pi over 3 and what's the one in quadrant 4? I've got 2 of them, right? I've got this one up here and I've got this one down here. 5 pi over 3. And now tell me where cosine is negative 1. Where is x negative 1? X is negative 1 here. Where's that value in radians? Pi. Yes, no, maybe. Okay, let's do this. This became this on the other side. Are you good with that when I moved it to the right? Okay. This became positive when I moved it to the other side. When I move the 2, I subtract 2. 1 minus 2 is negative 1. Yes? Okay, so we have solved using GCF factoring. We have solved using the square root method. We have solved using binomial factoring, where we had 3 terms that we brought down and we set each of them equal and we solved them. What's the only kind of quadratic solving we haven't used yet? Quadratic formula. Switch over to number 10, please. switch over to 10. Okay. At some point, you are going to simplify down to something that you cannot factor into baby parentheses, which means you're going to apply your quadratic formula, and you're going to get something that looks like this. First thing, do we recognize that this is two different solutions for theta? Yes, okay? This is two solutions. So the first thing we're going to do is we're going to solve this one. The sine of theta is equal to 1 plus root 3 over 5. The second is going to be that the sine of theta is equal to 1 minus root 3 over 5. Just like you would solve a quadratic and you would say x is equal to this or x is equal to that. Two different ones. How do we solve for theta using our calculator? And it involves sine. Inverse. So in your calculators, please take this out. We're going to do this together. You can take the best notes that you can so you don't forget to do this incorrectly. The way that I would do this problem with my calculator is I would, don't worry about this right now, put in 1 plus root 3 and hit enter. 1 plus root 3 and hit enter. Divide that answer by 5. Hit enter. Then put in sine inverse of the answer. So I would figure out what this decimal equivalent is. Then I'm going to take the sine inverse of the answer. What did the calculator tell you? What did it tell you? 300.12? 33.12. Okay. So the calculator told you this. 33.12. Yes? All right. This is where what we did in the warm-up comes into play. We were talking about sine. Is sine x or y? Y. So in this problem, okay, y is going to be a positive, correct? Y is positive? We know that because we went up. What other quadrant is y positive? Quadrant 2, right? So wouldn't the reference triangle be this dotted line? And the value of 33.12 would actually be there if we drew the reference triangle in quadrant 2. The issue we're going to have is that my answer here for theta, yes, it's 33.12, but then I also have this angle here. How much is that purple swoop? It's not 33.12. How much is it? Look at the diagram. You should be able to calculate it very quickly. 146 point what? 0.88 degrees. You have to know enough about sine to know that sine is positive in quadrants 1 and 2. So the question was asked earlier, is it always quadrants 2 and 4? No, here's one with sine that it's quadrants 1 and 2 because sine is the y value that's positive. We're only halfway done with the problem, but do you have any questions on either the work in green, using your calculator to generate an answer, or coming up with the secondary purple answer? Yes? 1 plus root 3. Hit enter. Divide by 5. Hit enter. Then in your third line of work, put in sine inverse of the ANS answer, which is the decimal you just found, and it should give you 33.12. If it doesn't, make sure you're in degrees, not radians, in the settings. Did you get it? Yeah? Okay. All right, so now let's put in the second one. Tell me what the theta is here in orange. Put it in your calculator. Tell me what the initial theta is. Calculator tell you? -8? Everybody got -8? Okay, so now if I come over here Negative 8.42 degrees. First of all, is negative 8 in the interval from 0 to 360? No. Okay? This is where the limitations of the inverse functions really kind of get you. So the first question I really want to find is not negative 8.42, but this orange swoop all the way around to there. How much is that full orange swoop? What do I get there? Theta is equal to 351.58. Okay, so we had to do a calculation in order to get it. The calculator didn't just give us the answer from the get-go. All right, before I go to the next answer, do you have any questions on 351.58? Sometimes when you're writing, you tune out, and all of a sudden you jump in and you're lost. Anyone have a question on 351.58? All right, so now, let's go back to what we did here. Here we said y is positive. What do we know now over here? Y is what? Negative. So over here we know y is negative. So if this is negative 8, guess how much this angle is over here? It's the same mirror image, 8.42. But now I want to find from here to here. That's pretty easy. How much is that? How much is the purple? 188.42 degrees. There's my secondary answer. So the solutions for this example 10, there are 4 solutions. Green, purple, and then orange, purple. Those are your 4. We have one more problem yet to do. We have to go back, but I wanted to do this one first because it's harder. And I think it's a pretty good example of all the stuff you have to be able to do with quadratic formula. Questions? No stupid questions, please ask. Anything you want re-explained. How did I, why did I, anything. All right, let's go back to example 5. Example 5, do you think this is linear or quadratic? 2t equals 3. That's what I see when I look at that without all the trig stuff there. Is that linear or quadratic? Linear. How do you solve a linear equation? Divide by 2. Isolate. Correct. So I've got tangent of theta is equal to 3 over 2. Well, this looked like the warm-up problem to me. How do we solve for theta? Inverse. So I'm going to do tangent inverse of 3 divided by 2. What do I get for theta? 56.31. Everybody get that in the calculator. Please put it in. Tangent inverse of 3/2. Okay. This is where the calculator work is kind of done, and now we need to go into our brains. So tangent is 56.31. So I'm looking here. This is 56.31. Here's the key, and I put the note on the board. There are 2 places that tangent is positive. Tangent is positive. It exists in quadrant 1 and what else? 3. If I draw the reference triangle in 3, this is 56.31. So how do I determine my other solution that I generated that's the purple swoop? What mathematically, when I look at my diagram, do I have to do to determine the size of the purple swoop? Add them together, what do you get? 236